sadly, we've come to the end of this unit 2 on the periodic table. So here's just kind of an overview of the trends that we've looked at. Now, the danger is that we don't want to just try to memorize this chart here and like, okay, electron affinity increases this way and it decreases that way or whatever, because that's not the kind of questions we're going to be asked. We're going to be given data, or we'll be told that, hey, the ionization energy of this atom is greater than that atom. Why? And we want to be able to explain why. And so a couple things on this chart. I mean, obviously the metallic character isn't anything that we really explain. It just kind of is what it is. That down toward the bottom, francium, bottom left-hand corner, that is where metallic character is the greatest. And up toward the upper right, like by fluorine and helium, is where non-metallic character is the greatest. In general, we just know that, I mean, there's this staircase, right? Kind of in here. Boop, 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 boop. And elements toward the left of the staircase are mostly metals. In the upper right-hand corner, that's my non-metals. And then along the staircase is my metalloids, elements that have kind of properties of both metals and non-metals. The other trend that I need to be able to explain is atomic radius. And so, yeah, I mean, it's helpful to know that, I mean, in general, the radius increases going down a group. And that's usually a trend that kids get right, because they understand the fact that as I go down the group, there's more energy levels. And if there's more energy levels, then, yeah, the electrons are farther from the nucleus. The atom is bigger. If you're going across a group, the atomic radius decreases. If I'm going across, I'm adding electrons, but I'm just filling like the second energy level. But going across then from left to right, as I add another electron to the energy level and another proton to the nucleus, the attraction increases. So going across, as the attraction increases, the atoms shrink a little bit. That outer electron shell is just kind of pulled in toward the nucleus a little bit more every time I go across from left to right. So the other two that they kind of mention in question 18 here are electron affinity and ionization energy. Question 18 says that they appear to be opposing concepts, and I would agree with that. They're both energy, so they both represent a type of energy. Here's ionization energy. Let's see. Well, I'll do this first. Electron affinity energy. When I think of electron affinity energy, it's energy released when an electron is absorbed or an electron is gained. So I could have element X, and I add an electron. I form then the X minus 1 ion because I gained an extra negative. But in doing so, I would also release energy. So releasing energy means that this change is exothermic. Energy is produced. Energy is a product. Energy is released. This is an exothermic change. A little different is, my friend, ionization energy. Ionization energy is an endothermic value. It's where I have an element, it could be element X, and I add energy to remove an electron. I mean, think about it. A negative electron is attracted to the positive nucleus. And so it's like magnets that are attracted to each other. If you want to pull apart strong magnets, then you have to add energy. And so here, if I want to remove an electron, I have to add energy. This is an endothermic change. When I add enough energy, I can remove the electron. That would leave me with an extra proton, so a +1 ion, and I would release the electron. So yeah, I agree with this first part of number 18, that they do appear to be opposing concepts. I mean, one of them gains energy, one of them releases energy, one of them forms a positive ion, the other forms a negative ion. One's about losing the electron, the other's about gaining the electron. Absolutely, they appear to be opposing forces. But now if we look at the main group elements, which main group just means basically the S block and the P block, because the D's don't follow trends great, and obviously the F orbitals on the bottom, these are atoms that are highly unstable and radioactive. So main group kind of just means like referring to the S block and the P block. Why? Explain why both share similar periodic trends in a period and a column. And so, for example, like it's easy to see the red and orange, or the orange and yellow arrows that are both increasing, going across. And they're both increasing, going up a group. Okay, so let's think about this. And we really have to understand like what these terms mean then. Going across. So as I go across, they both increase. Well, I mean, if you're ever like in doubt and you have to answer a why about a question that has to do with periodic trends, I guarantee the answer is going to have something to do with Coulomb's law. It's going to have something to do with the degree of attraction between the nucleus and the energy levels, the electron cloud. Okay, so as I go across, let's think about this. I don't know, I'll go red. Going across. See, across a period. Okay, so going across, I know that according to Coulomb's law, the distance is essentially staying the same because as I'm adding the electrons, they're just going in the same energy level. But I am increasing the magnitude of the charge. And so Coulomb's law had the magnitude of the charge in the numerator and the distance between the nucleus and electron cloud in the denominator. Well, that's basically saying the same. But the magnitude of the charge increases going across. I'm always adding another proton, I'm adding another electron, and the attraction increases. Attraction increases. Magnitude of the charge increases. Magnitude of charge increases. Okay, so let's think about that then. If the attraction is getting stronger going across a group, well, yeah, that would make sense that the ionization energy would increase because you have to gain more energy then to remove an electron. But if the attraction is also increasing within the atom, the nucleus has become more positively charged. And so obviously then the more positively charged nucleus is more attracted to its own electron cloud. It might even be able to attract a neighboring electron. The magnitude of the charge increases. The nucleus, I'm going to write this. The nuclear charge increases. I could have kept that. Nuclear charge increases. And so actually because the nucleus is becoming more positively charged, it affects both of these in kind of the same way, that if the nucleus is more positively charged and there's a stronger attraction within the atom, then it's more likely that I'm going to gain another electron. And if it's more likely that I'm going to gain an electron, it's more likely that I'm going to release energy. But on the flip side, if I wanted to remove an electron, then if the attraction is stronger, I'm going to have to add more energy to remove the electron. They both go back to the fact that the attraction is increasing. The nucleus is more positive, there's more protons, the magnitude of the charge is increasing. This is like big time. It's big time chemistry. That if there's a greater attraction, it's more likely that we'll gain an electron. which then would release more energy. But if I wanted to remove an electron, I'm going to have to add more energy. The attraction is stronger. Okay, so now think about this within a group going up and down. So within a group going up and down, it looks like the ionization energy and electron affinity are strongest at the top of the group. Okay, well, let's think about what's happening at the top of a group. So let's, I guess I could, usually I write this as going down a group. I'm going to do that. I'm going to say going down a group. Going down a group. Okay, so going down a group. We got to get one thing kind of cleared up. Going down a group, you're adding energy levels, right? I think everybody gets that. We're adding energy levels. So the distance between the nucleus and the electrons is increasing. Distance between nucleus and electron cloud increases. Okay, so the distance is increasing. That is the number one factor that is going to affect properties within a group going up and down, is the fact that you're putting electrons in higher energy levels. Now, somebody asked the other day, and it was a really good question, and they said, but you are like adding more protons. Like, if I look at lithium, there's an atomic number of 3, so there's 3 protons and 3 electrons. And then if I go down to sodium, there are more. So it's like 11 protons and 11 electrons. And potassium is even more, 19 protons and 19 electrons. And so somebody asked a really fantastic question. And they said, well, but doesn't that mean that like the nuclear charge is also increasing? And if the nuclear charge is increasing, then doesn't that like make the attraction stronger and shrink the atoms? Oh my gosh, such a great question. If we were to go all the way back to Coulomb's law, oh my gosh, Coulomb's law, I'm obsessed with you. Now, I will never ask you to calculate anything with Coulomb's law. Here it is, right in the middle, Coulomb's law. I'm never going to make you calculate anything with Coulomb's law. But it doesn't hurt to just kind of understand it. Number one, so yes, charge goes on top, but technically it's d squared on the bottom. So like it's distance squared. And eventually that has a huge impact on the degree of attraction, this force of attraction, F. And so like d distance would be measured in usually like picometers or nanometers, like some teeny tiny fraction of a meter. It's the distance between the nucleus and obviously like the outer electrons, but we're going to square it. And so that's going to have a huge impact on the force. And so if I end up putting big numbers in the denominator, it's going to make the force really small. And it's the force of attraction. And so number one, distance is technically squared in this Coulomb's law equation. But then number two, think about this analogy of like an NFL stadium. Think about Lambeau Field or any giant stadium for that matter. The nucleus is a tiny marble in the middle of Lambeau Field. And so, yeah, I put a couple extra protons in the nucleus. But the electron cloud is huge. And so, like, adding 1 energy level, 2 energy levels, 3 energy levels, it makes a huge difference. Like, distance is a huge factor going down a group. And so, yeah, you're putting more protons in the nucleus, but you're putting the electrons way farther from the nucleus as you add energy levels. And so whoever asked this question, I'll leave them anonymous. It was a fantastic question because it made me think that, gosh, they're really understanding these concepts of increasing electrons and increasing energy levels. And so it's not wrong. Yeah, we're adding more protons, but distance has such a huge impact when you're putting those electrons in farther energy levels. It far outweighs the fact that, yeah, potassium has more protons than sodium, but it's trying to hold on to electrons that are going way far from the nucleus. So the number one factor that affects any trends within a group is distance. Going across a group where distance really is not a factor, then it's magnitude of charge. Oh. I hope that kind of clears things up a little bit. So if I know then that going down a group, I'm putting electrons farther and farther and farther from the nucleus, well, that makes sense then that the attraction is weak. I'm going to say weaker attraction. Weaker attraction. Okay, and so if the attraction is weaker, then yeah, I'm not going to have to add as much energy to remove electrons. It doesn't take much energy to remove electrons from big giant atoms. The electrons are super far from the nucleus. And so, yeah, the attraction is weak to start with, so it doesn't take much energy to remove an electron. But along the same lines, think about it going down a group where you got these big atoms and the attraction is already really weak. Do you think that they're likely to gain electrons? Probably not, right? I mean, these big guys down at the bottom have a hard enough time holding on to their own electrons. The chance that they're going to gain electrons is highly unlikely. So if it's unlikely that those big atoms are going to gain electrons, then it's unlikely that they're going to release any electron affinity energy. And so yeah, the trends do kind of, even though they're real opposites in concept, they do kind of follow the same trends because they both hinge on the degree of attraction between the nucleus and the outer electrons. And so with that then, I do not need you to do number 19. Cross that one off. And really then at the end, between 20 and 21, the only one that I want to focus on a little bit is 20. I mean, 21, we're not studying minerals. We can skip that one. But 20, I think, is kind of interesting. That we've always been told the noble gases are non-reactive. And for the most part, it's true. And for the most part, it's true because they have their full orbitals, right? Their outer electron shell is full, so they really don't need to gain electrons or lose electrons. They're pretty stable. Of all the noble gases, helium and neon are completely inert, which means non-reactive, and they do not form any known compounds today. However, some of the heavier noble gases like krypton, xenon, and radon are capable of forming a few compounds. Often they'll bond with halogens. So there's like a krypton chloride and a xenon chloride compound. Using periodic properties and electron configurations, explain how this can occur moving down this group of elements. Well, I mean, think about it. I don't know if we have to draw an electron configuration, but think about it, going down a group. When we get to like krypton, xenon, and radon, we're talking about some pretty big atoms that have electrons in 4, 5, 6 energy levels. Okay, so I'm going to make note of that first. Number 1, krypton, xenon, and radon are large atoms with electrons in many energy levels. So in a sense then, we're saying that the electrons are really far from the nucleus. Well, if I know the electrons are far from the nucleus, that causes a weak attraction, right? There's a weak attraction between the nucleus and the electron cloud. And so guess what? Even though technically the orbitals are full, if the attraction is weak, I mean, think about like xenon, radon, 5, 6 energy levels. The attraction is weak, so it's possible that we might lose an electron. Very possible. Just because that poor nucleus is trying so hard to hold on to its electrons, but they're so far away. And so it is possible that you could lose electrons. And if you lose electrons, you form a charged ion. And those charged ions will be attracted to other ions with opposite charges. And eventually what we'll find in the next unit is that results in a bond or a compound. When you have oppositely charged ions that are in the close vicinity of each other, there's a good chance then that they would form a bond. So yeah, because of that weak attraction down at the bottom, the atoms are so big, it's highly likely that they could lose electrons and eventually then form a bond.